think last class the second half video got disconnected. Somehow we lost the data. If someone has it, then that would be great. Someone else can also start recording. Maybe if I'm not able to record any of them, then we can go through it. Yeah, I can say. Okay, I think last class we covered static cast and dynamic casting. This class will cover constant casting and reinterpret casting. Okay, I think type name, type ID, we all covered. It's solving problems on performance. I mean, they all are part of this. Okay, so okay, so what is constant cast? Casting you would have seen in C code wherein you can uh, change the cast of an, I mean, say change the type of an a variable from int to something else, into char and all. So in the same way, you can change the constantness of a variable also, like const to something else, non-const to constant and all. Okay, so 25. So what does C++ provide? What is it uh, that const key character provides so much that is not what C provides? We'll see this in this class. Okay. First thing is that you can have a class, okay, in which you can have a function which is constant. Okay. You can have a class in which you can have a function which is constant. Okay. You see the moment you declare a function as constant, what does it do? It will not let you change anything with respect to the class. Any variables that you have, right? It will not allow you to change. Okay. But const functions changes the role. I mean, we can change it or we can do it with the help of constant cast, yes, and all. So you can just call this function func, and using which you can change the content. You can assign it and see what happens. We'll just run through this example. You guys can understand this better. So in this example, I will just remove this. Okay. Let's not complicate this. We'll just say roll is equal to 5. What it is? It is just a roll is equal to 5. Since the function is constant, okay, this is not allowing us to change. So what is the other way? Either we can change it. The moment we remove the constantness, it will allow us to change. We will not see any issues here. Okay. But the moment we put const back, we get error during compile time itself saying that you are not allowed to change the constant variables here. Okay. So to overcome this or to bypass this rule, okay, to bypass this rule, that is when we can use it. But also that you need to see here is you are typecasting it to whole class. You are actually converting this pointer to some integer pointer. Actually, the role is a local variable which you are trying to convert it to some class pointer. Okay, and you are doing some type conversions from this to student star and actually this. student object, right? Okay, so you are just converting the student object from which is non-const to const, and you are trying to make a changes here. Okay, we'll see what happens with this. Just compile this. Okay, if you see, we created an object of type student here. We assigned some value 3. Okay, this is a parameterized constructor which is just taking 3, and we are just trying to print it contents. So this will just print the content of this value. Now we just called a function which is a const function, but inside that we made some rule to change the constantness of it. So this function, with the help of this function, we are trying to convert this pointer from const to non-constant type, and then we are able to change it. Okay, so basically this is used to convert const to non-constant and non-constant to constant. All these types we can do it, and we can make changes to this. Okay, so it is just like any const to non-constant conversions. Okay, now in other. Okay, so what is it that we are doing here? I'll repeat again that this pointer here is a const pointer. Okay, by using const cast, we made it. What did we do? We made it a non-const pointer, or you can say this pointer is a const object pointer. Like, so you are not allowed to make changes inside this function, inside a constant function with the help of in any way. Okay, we are not allowed to make any changes. But the moment you put const cast, what happens is that this pointer that you had, right, you are trying to convert it to a non-constant type. So constants will become non-constants, non-constants will become constants, and we made it non-constant, since we are able to make changes. Okay, am I clear on this one part, guys? Any doubts on this? So we just made this pointer as a non-constant pointer. Okay, only because of that we are able to change it. Now let's see what happens if we just remove the constant from here. Okay, it's still compilable, and it gives the same result. Okay, so whether the const is there or not, the moment you use the const castness, the constantness of this is lost, and we are able to make changes to this. Okay, now let's see one more example what they talk about. Okay, const castness can be used to pass const data to a function that does not receive constants. Okay, what it means is, you can have a function, that does not receive constants, or in the example following, okay, So if you see here, what do I have? I have a value, integer value, which is of type constant, which is of type what? Constant. Okay. So can anyway we can change this content? Can we change the contents of a val by any chance? We cannot change the contents of this val by any chance. The moment you try to do it, it will give you error. Okay. Now, what if we typecast it to something else? Now we have a pointer by name ptr, which is trying to point to the object by name val, which is a constant. So in order to point to this, what would we need? A pointer. Can we see? Let's see whether we can use a int pointer to it. Normal integer pointer. See, the data is int. Okay. Can we use a int pointer to it? No, it says no. Because the moment you make it a int pointer, you are trying to say this address is modifiable. You are trying to say this address is modifiable with the help of this pointer. So what would you would do in your code? You try to match the data type. What would you do? You try to match the data type. Okay. So you make it as const int pointer here. Okay. Now what kind of operations you want to do on this? You can just pass it to some other functions who would do some operations on top of this. Okay. They would not change it, but assume that they need the pointer. Okay. Now, okay. Now you have a function which is trying to take, you have a function which is trying to take the PTR. Okay. Now function PTR, what it is taking? What is its argument? It is just int pointer. It is not a constant point. But PTR is constant. Whereas here this is not a constant int. Okay. So he is giving us errors. Like I am allowed to take only constant objects. I am not allowed to take non-constant objects. Okay. So to overcome this, temporarily we are going to change a constantness. Okay. What we are going to do? Temporarily, C++ provides us facilities wherein temporarily you can make the object as a non-constant, the pointer as a non-constant, but the content will go ahead and remain as a constant. Now, if you see here, if you actually see here, you made you created one more pointer ptr1 out of this. So you just remove the constantness and assign the value to it. You just typecasted it from const integer pointer to a normal integer pointer. So you are just trying to take out the constantness from this pointer. Okay. And let's try to pass it. Okay. ptr1. Okay. Now if you see, this thing absolutely compiles. You are not seeing any error. You can try compiling this and see if there is any error that comes out. Okay. So this guy compiles. Let's see what is the output. Sorry. So the output is 20 here. Okay. Let's make it proper. Okay, you see the output is 20, which is nothing but 10. Okay, and you took the pointer. Okay, and this is just a temporary value, so this will be just replaced with 10 plus 10, and that content is written, the sum is written. You are not changing the content of PTR, you are actually just passing the value, okay, with the help of pointers, without a need for constantness. Okay, so tell me, guys, where can we use this constant case? Like, why can't someone go ahead and change this as const? Why can't someone go ahead and change this const? So anyone, why can't we just go ahead and change the const? When or when can we get into a situations where we are not allowed to change this from int to const? Like situations where you are not allowed to change. So it's just a code. Anyone can go and change anything. Okay. Anyone can tell me. Mhm. I don't see any answer from anyone. Okay, I'll tell you. So assume this function is a library function. Like this is a library function or written by someone else, for which you have only read access, and you are not allowed to change any part of the code for this. So this function is in some other file or some other library, okay, which you are not allowed to change. That's when you can do all this magics, uh, and still continue to use this function. Am I clear on that? Any doubts on that? Why we wouldn't use this constant conversion? It is just trying to remove the constantness from the pointer. Okay, it is just trying to remove the constantness. That's all. Okay, but does it mean can I change the content of this? Hmm? So I just remove the constantness. Does it mean am I allowed to change the contents like star ptr is equal to 30? Okay. Am I allowed to do this? Let's see what happens. See, the behavior is undefined. So you are able to actually change the contents. You just removed the constantness here. You removed the constantness from this and you made it such a way that you can change the contents of this temporarily. Let's see what happens here. Now, if you actually see that the results are different. Now, what is this 40? 40 is what this functor has returned. Okay. So technically, the PTR is pointing to what? This constant memory location. It is pointing to this constant memory location. Now, what is this memory having? It is 10. Okay, it is having 10. And what did we do? We passed the value 10 to here. Okay, the pointer which is here is still pointing to a memory which is having 10. Okay, but what did we do? We overwrote it with some other value. Since we have access to the memory, we try to change the content. Okay, so what is the content we made? 30. Now 30 plus 10, what did we do? We made it 10. Actually, we are not passing by value, we are passing by reference. So we are able to make changes here to the pointer, and the result also it came. Okay, here. This is where we are printing the results. So what it should print? It should print 40, and it is printing 40. 30 plus 10, which is 40. Okay. Now using the same PTR, okay, which is pointing to int star, and we assign some new value as 50. Okay, we assign new value 50 into it, and we try to print it. Okay, we try to print it. Now what it is happening? We got the value as 50. Okay, but the 50, where should this 50 go on sit? This 50 should go and sit in this value, right? But what is happening here? I just printed the content of value, and it is printing something else, which is 10, which is what it was initialized. It's weird, right? This behavior is completely different. So the way the memory is still have holding 10, but the pointer through which you are trying to point to this itself is what should I say? Giving some different value. Okay. Now let's see. We'll remove this constantness here. Okay, and see what happens. And we compile this. See, the constantness is removed here, but and the value got changed. How did this happen? This is completely weird, right? Like you just remove the constantness. The same memory location is having 50 and 50, but you retain the constantness. Okay, the memory which at which it is pointing is still holding 10. Okay, so there is some different behavior, undefined behavior that that can happen when you are using the constant cast, when you are trying to make changes to your code with the help of const cast. Now let's see what is the behavior of this with different versions of C++ compilers. Now with the plain C++, what it is giving, it is giving 40, 50, and 10. Okay. Now let's see with C++ 20 what it is trying to do. It is same. So the value remains same no matter what compiler it is. The constantness on this memory location is not lost. Okay. Am I uh, clear on this, guys? Any idea? So the point that I'm trying to make is, use when you typecast this pointer, okay, from const to non-const, okay, and try to do some operations, the behavior is not defined. Like it can happen anything. Like you are expecting something and the result is something else. Let's let's try to print the address of them. Are they pointing to same memory locations or not? Let's see. See, it is pointing to the same memory location. The address of val is also 64F4. The pointer is also pointing to same 64F4, but the results are different, 50 and 10. This is a weird behavior that can happen, okay, if you are trying to make changes. Okay, now let's see if I comment this part. Now let's see what happens here. So PTR is 30 because you assigned here as 30. Now let's see if I'm not doing anything here. The address are still remaining same. Okay, see, the content is retained. It is pointing to same memory location. The data remains same. Okay, now the behavior is completely different here. Okay, you got this right? I'll save it here. Maybe you guys can try to understand what it is. Okay. Okay. Now let's go through another example with respect to this. Let's see. So it is trying to say, I think it is the same thing which I have explained, wherein the behavior is undefined if you are trying to change the content. Okay. Next, const is considered safer than simple typecasting. It is safer in the sense that the casting won't happen if the type of cast is not. Okay, let's see this one. Okay. So what we are trying to do here is, in the third example, is we have a variable a1 which is declared to 10. Now we have a pointer which is a constant pointer, okay, which is pointing to a non-constant memory location. What is it pointing? It is pointing to a non-constant memory location. And what we are trying to do here is, the pointer is int, but we are trying to typecast from int to character. You are trying to typecast it from int to a character. Okay, this is like you are generally if you remove this, so this should allow you are not seeing any issues here, because int pointer is pointing to a memory location of 4 bytes. So new spreadsheet. Okay. Now int will have 4 4 bytes in the memory. Now what does it have? It has 40 in it. It has 40. Now you declared a pointer by name b1, which has address of 1, 2, 3, 4. Okay, which has address of this, and using this address you can make any changes to this content. Now you declared one more pointer c1. What is this? C1. And what did you do? You just assigned the contents of b1 to c1, and you said c1 is a character pointer. So what will this have? This will also have this. This will also have this. But let's see what uh, it will print when using what. Can have it another way also. Let me print the address and the value as well. So what we are trying to do is we are trying to print the value of the pointer and also the content pointed by the pointer. One and C1 of A. What happened? Okay, we okay. So what did it do? Okay, what it did is C1 has become a variable. Now what did you declare? C1 is we declared it as a pointer, but it actually became a variable. Now if you are trying to print the contents of C1, it is printing as A. Okay. So if you are trying to print the content of C1, instead of printing the address, it is printing the value. And even if you're trying to print the memory location pointed by C1, it is still trying to print the value, which is A. Okay, in both the places you see the behavior is completely different here, right? It is uh, weird because what we did is we converted it from int pointer to char pointer. Okay, so now let's see. We'll retain this constantness and see what happens. See, the moment you try to change from int pointer to char pointer and all, the compiler itself is giving you the errors. So this is not something which C++ would allow you to do, and it will always give you those errors. So this will not even let you compile. See this, it will not let you compile this code. So but the same thing you are allowed to compile by just removing this const castness. So the undefined behavior that you are seeing here, right, is lost. Let me make it C2. Okay. So am I clear on this? So with the help of const castness, the undefined behavior that we saw in this one and in this example, previous example, and in present example, we can identify during compile time and we can fix those issues. So that's what uh, this constant castness provides as part of C++. Any more questions on this, guys? Anyone understood or never understood or completely blank on this? See, do we have another? This is where it explains in detail. You can see this also. Before I go through the next example, like what it does or actually does, if you have any questions, let me know. So basically constant cast or dynamic cast, okay, or static cast, all these are used to identify the problems during compile time itself. Okay, by any chance, did you write a code which is uh, which can lead to undefined behavior? Okay, all these things you can identify during compile time itself. That is not something which is allowed or which you can find during uh, 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 you cannot find those problems in C. This is something which C++ provides us. Okay, so you see all these errors during compile time itself, the wrong way of coding. Okay, so all the bugs, unknown bugs or weird bugs that we see in C can be avoided in C++. Let's go through the other one. So here is where we can understand what it actually does. I think that's a reason you would like to know what the power of type ID is something which you would come to know here. Okay, so the so the fourth one is const cast can be used to cast away the volatile attribute. Okay, so what does volatile mean? It can be used to remove the volatile. property of a variable. So if you see, this is an integer of type int. Okay, this variable a1 is of type int. Okay, now I just declared a pointer. Okay, const volatile int pointer. I just declare const volatile int pointer. So what should be the type of this? Okay, const followed by v, now pointing to integer. So what does each word say is I is integer, and after that you see pointer. So that's why they say pointing to an integer. Now we added one more keyword by name volatile and then constant. So volatile, you guys know, right? Uh, Anyone know what does volatile mean? So basically, volatile is deals with multi-threaded programming. Okay, so in multi-threaded programming, compiler can do optimizations on your code. Like uh, thread one can in thread one you can declare or initialize the value of this, and on thread two you can monitor it. Okay, so
Sir, it's also qualifier means we can
sorry.
change that. Once we declare any variable
Hmm.
with volatile,
Hmm.
we can change that value of that variable further in programming.
Correct. See, it is like a normal variable itself. So if I just remove constantness, it becomes a normal variable. So what does volatile mean is you are telling the compiler to remove any optimizations that the compiler does on this variable. Okay. So what it actually does is, so if I have a int a is equal to 1, okay, and while a, right? So what would compiler do? So what would compiler do is it would try to optimize this code. It would try to optimize this code. The optimized code will become, so I'll assume these are your instructions. So the optimized code will become something like this. Okay. So this will be the compiled code, but on editor you will just see this. Okay. But if you make it volatile, okay, this kind of optimization is not introduced by compiler. So your code will try to remain same. Okay. So the previous okay, I'll remove this. Okay. So without volatile keyword, compiler will convert your code, whatever that you have written inside, to this. So all the 1, 2, 3, 4, and 5 lines of code will be replaced with 1. Okay. But if you put volatile keyword, any optimization that compiler performs will be avoided. Okay. So generally when we'll use this is you will use a inside this you are trying to create a thread. You are sharing a this variable to that thread. Okay. Now that guy is going and changing some contents onto it, right? That's when, okay, the behavior of your code will become completely different. Okay, so that kind of unknown bugs you don't want to see in your code. Okay, so that's why you will have this. Okay, am I clear, Lipsa? Lipsa or who asked this
Yes,
question?
sir.
Okay, I'll just remove this. Okay, now we'll see. So what does this is? So we are just trying to print the type ID of B1. Okay, we'll just type to print the type ID of B1, and we will try to convert the same pointer ka B1, and we'll just try to remove the constantness and see, and we'll print the uh, uh, type of C1 and see what happens. Yeah, let's save this. Okay, so what does this four value that values that it printed mean? It is P. P means pointer. Okay, it's actually a pointer. V means it's a volatile. K means the constant. I means finally I means the integer type. Okay, now that is what this line has printed. Now you did a constant cast on top of it. Okay, so it will just remove the constantness and will give you int type, constantness and also volatility you can remove. So if I can still make it volatile and see if we can do this, try to do this. Okay, see, it is just removing k, the constantness. Let me be, see, the difference between previous one and now is the volatility is retained, only the k, the constantness is removed here. Okay, now let's see, can we still keep it as it is? See, it is just retaining as it is. So whatever that you mention here, okay, that type of conversion it will do. It will try to convert it to that type. Okay. So now let's see, we can remove volatile here and keep it as constant. So it is giving an error because what you have declared here is not matching here. We'll just remove that and see. Now what it should print? K of I. K of I is nothing but constant and integer. Yeah, pointer to a constant and integer. That is what it is trying to do. Okay. Am I clear on this? Any doubts? This is a tricky. All these are like tricks um, that you can understand. Okay. All these are just concepts. You can apply when and where it's required. Like if you know these concepts, you can just apply. That's all. All this something is not something which your C will provide. Okay. So the next one I wanted to cover is reinterpret cast. Anyone know reinterpret cast? Or anyone has used library ever?
No, sir.
Okay. So what does reinterpret cast provide? Okay, and how dangerous it is. Okay. So the reinterpret cast is generally is used when you are working in a project which has C and C++. Okay, if you are working in a project which has C and C++ in it. So let's try to do something. What should be the number? 27. Okay, let's take this example which is here. Okay, what he is trying to do. So you you might have seen code. Let me copy this code and just have some hello world. Okay, let's go through this, then we can try to do something. So reinterpret cast will tell the compiler. Reinterpret cast will just tell the compiler to blindly convert an int star. I mean a particular data type. I mean whatever, no matter what the pointer is pointing to or what type of object it is, it will blindly convert it to whatever type that you actually want. So whatever type that you actually want. Let's copy something from here, this type ID, and see what is the behavior here. Now what is the what type of pointer is P? We'll see what is the type of object P is pointing. Okay, now we have two pointers. One is P, the other one is CH. Okay, before we get into next result, we'll just see what kind of pointer that this guy returns so that we'll understand this. Now if you see type ID of P, what is the type ID of P? P is nothing but int pointer, whatever that you have declared, P of I. Okay, now you have something else by name, some other character by name, character pointer CH. What is the type ID of this? CH. It is pointer to character P, C. P means pointer, C means character. Now this is P of I. P is pointer, I of, and I is int. Okay. Now in the previous topic, right, we tried to do something different here. What did we try to do? We tried to take an int and what did we try to do? We tried to declare an int and we try to have a int pointer and we try to convert it using constant cast and all, right? There we found issues. Okay. Okay. So what is the difference between that and this? It's purely nothing. Let's okay. Now this is a const int, right? Constant, and this is a constant pointer. With help of constant casting, we are not able to convert it, convert it to a character pointer. Okay. Now let's see, can we do the same thing with the help of reinterpret? Okay, cast, reinterpret casting. Can we do this? Cannot cast away constantness or other type of qualifications. So it can still cannot cast away the constantness. So, but can it at least convert this to char. It can still convert this to a char pointer. Okay, it can still try to convert it to a char pointer. So, but can this thing do? See, on the same variable, you cannot do a constant casting. So you cannot convert a integer pointer, const integer pointer to a const char pointer using constant cast. Okay, but you can tell the compiler to reinterpret it and do it. Okay, but you should, but the reinterpret cast comes with a clause saying that it is extremely dangerous to do any such things. Okay, so because you are trying to see this as a what should I say, constant character, and you can do anything on top of it. You can you can make changes at all also, because all those clauses comes here. That is some dangerous part that we are trying to do. So, but you guys are able to understand this part, right? Like using constant cast, you are not able to see a plain const int as a char. Like assume you have a memory location, like a memory wherein stored you have a series of bytes. Okay, so it's an integer, okay, which is having an MSB having value 1, uh, MSB followed by the next byte, followed next byte is having 2, next, not next byte, next nibble is having 2, and this is having data something like this. Okay, and you are trying to get data from here, like this byte and this byte and this byte and this byte. Okay, how you can read byte by byte of an int? You can just typecast it to, you can create a, you can create a reinterpreted character pointer. You can use a reinterpreted character which can point to this, and star of C1 will point to 1. Now star of C1, 1 plus 1 will point to 2. Okay, now star of C plus 2 will point to 3. Point to 4, and so on. So with the help of this reinterpret or this pointer concepts, right, you can actually see the content of integer byte by byte wise. Okay, we will go through that. Okay, this is what this is the capability that this reinterpret cast and everything gives us. Okay, now let's am I clear on this, right? The behavior of this. Okay, I'll just show you the demo also now. Okay, so we'll go through this now. Assume this 650, right? Two, okay, 01, 02, 03, 04, maybe. Now let's see what P points and CH points. Okay, now next. Next we will do, we cannot do P, we will do we are just trying to see whether we can do this. Now what is the behavior? We'll see. I just printed, but what did it print? It is not able to access. Type ID, it just printed the content point, address of B, address of C, but it didn't print the values. Okay, it is in hex. Okay, here it printed the type. Next, using star ptr, the content of memory pointed by P, it printed 1 2 3 4. Now we are trying to see it as character, and it just printed it as star. Now this is an integer. The value that it can store can be completely different. So let's have a value C in it. Now if you see the content of P is what we stored, which is ASCII value of C is is 99. Okay, so it printed 99. Now you can see the same content. You just type converted the int to character with the help of reinterpret cast and try to see it, and it is trying to print it as C. Next, what we did is we just incremented the CH. We incremented the CH, and what it did, it printed the address, maybe a new address. Okay, but and when you try to print the content, it is showing as C. But if you see on top, earlier it didn't print the content of, oh, this is okay, sorry, this is this, and this is this. Oh, it is actually converting this into, is showing it as a variable itself. It's not even actually trying to convert it as a pointer. Okay, so 99 and C are the data that it is pointed by. Okay, the P is the memory location at which the C is stored. Okay, now CH, which is supposed to be a pointer, and it is supposed to print the address. It is not printing the address. It is actually printing the content that it is pointing. Okay, you got what I'm trying to say. So whether you are doing a reinterpret cast or const character cast on anything, right? The type ID can show as pointer, but when you try to print the address of it, it will not print the address. It will actually print the value itself. This is completely different or weird behavior that just happens with the casting and all. Okay, because you are trying to increment and do on all other junk activities here. Okay, so the you should know the this behavior. So when you are using any casting, right, uh, you should be very much aware of what you are actually trying to do. Okay, now let's see. Let's declare the same ch and just remove the reinterpretation here. Okay. Isn't the behavior same? Or did I save this one? Yeah, I saved the file. I think the behavior is same. Whether you have reinterpretation or not, it is still printing the content and not the address of it. Okay. So when this reinterpret cast is used, that's a main question. So I'll add a file. That you will understand. So I can write a function which takes void pointer. Okay. And to which function or function see. Okay. I have a function which takes p. Now what type of value is p? That what matters for us. Now p is an int pointer. It is a pointer which is pointing to it, to which we have assigned some integer value and all. Now you are trying to pass it. Okay. Now function one is a, assume this is a C function which is taking void star. Like in C, you can have a function which can take any type of data with the help of void. Okay. And you are trying to reinterpret it to something and print it. Okay. Now we'll see what happens. So what did I do? I declared a function in C, I mean a function to which we are passing int star, but the function actually take void star. Okay. Now what we passed is a void star. Okay. So here we are passing int. Now tomorrow someone can write a code to pass char or anything. He can pass anything that he want, but we should typecast it to the type that we need and use it. Okay. So actually this is not a function in C. This is a function in C++, which which is called by a main in C. C code calling C++ and C. Okay. So assume you have a C++ code. You have a C++ code which you did some extern and all. Okay, and C application is trying to use your C++ code. C application or which C code is trying to use your C++ function. Okay, so one thing that C++ provides is function overloading. You can have a function overloading parameter, right? You can have something like this int star, and you can have something like this star star. Okay, so this looks completely fine. You can have a function int star and char star in a C++ code. Okay, but can you have that in C? Can you export this into C? No, because C does not support function overloading. It doesn't understand them. It doesn't understand all this part. So if you have a function which can take different types of arguments, okay, different types of variables. So what you do is you use a void star pointer. So you make this function compatible with C. So you make it as a void star and you pass it here. Okay. I mean, and you give this function to your C developer or someone, and you ask them to use it. So he will create data type of his interest. It can be int, it can be a structure or anything, and he will just make a call to it. Okay. So, but once he makes a call, that is when you should also know that you will be converting the data type that he passed to the data type that you are expecting. Okay, you should know like that he would pass only int or character, and then you will use it to what you want. Okay, what type of want you want, because you should be sure like what type of data he's passing, and you should put that in to interpret as this is that of this so and so data type, and I am trying to use it in my application. Okay, so he can have a some dummy structure also here. Okay, and he can pass it. You can create a you should actually have a void star conversion here is showing some compiler issues because we should have some operator overloading here. Something like this now. And not be able to exactly replicate it. Okay, that's what's going on. So using this, see, using this reinterpret cast, you can just convert a known data types to compatible data types, and we can use them as we want. So generally, your C++ functions can be exposed to a C apps to use it. Okay, so that's the purpose of this. Or C structures can be called with the help of C. Okay. I think that's all I wanted to cover. Anyone has any more doubts on this? Where did pass address? I think I was not passing the address. That's why it did. He was pointer. This was not okay. So we can pass anything of any data type. You can. So your C++ function can take a structure created by a C code. Okay, and you can pass it using void star, and you have to use it explicitly. You have to declare it pointer to structure. It's actually not implemented. We cannot print that. It's not a printer, printable object. Okay, so you can use this pointer to print the contents of it. So it can have okay. It's a pointer, right? It goes like this. Okay, you can comment this and see that using this typecasting, we can actually do the operation that we want, but we should comment this part. So what was the value that we initialized this to? 0, it got printed 0. Now let's make it 8. Okay, it printed 8. Okay, so with the help of type reinterpret cache, we can convert data of any type to any type. Okay, now let's see in the same code if we enable the other types, the behavior. So here we are just passing structure. We are passing a structure which is bigger than, which can be bigger than this, and see what happens when we are trying to point here. So what has happened here? You see a different behavior. You sent a structure. You actually sent a structure. Okay, and ch is trying to see this structure as a char star. Okay, see this structure as a char. Now what is the content of this structure? It is nothing but an int, and uh, it is trying to see this as an int, and it is trying to point, to the start. Now what does this int has? It has 8. The 8 will be sitting at the last. Okay, first 3 bytes will be free. At the 4th byte is where the value will be stored. Okay, the value 8. So that's the reason it is not able to uh, print anything, whether it can be garbage or anything. It is not able to access it. Okay, but you read now in the second case, you are trying to see the structure as an int. What you're trying to do, you are trying to see this structure as an int, and when you are trying to do that, okay, it is printing 8. Now if you see, when you with the help of pointer pi, with the help of pointer pi, you are trying to see this as an int. Now the structure has only int, so it has complete access of this. It has complete access of this, and it is trying to see this as a int and print it. So since he had complete access, he is able to print the complete contents of this. Okay. Now the third one is again, it's a reinterpret cast out dummy. The structure to structure, it is matching, and you are printing the variable out of it. Now let's see what happens if you make this as a character. Okay. See, now I just made this as a character. What did I do? I just made this as a character and I compiled it. Now you see the result. The behavior is undefined. Okay, the behavior is undefined. The structure has character, but inside that, even the you try to make it as a char pointer, it is not able to print the contents. Now the second one is this one, p of I. Why is it saved or not? It is saved. Now you used a pointer using which you are trying to see this as a int pointer. Now this int pointer, what it did, it got access to memory location beyond what this structure has. Okay. Now because of that, even the reinterpret cast is not working. See, in this case, this should work, right? Now let's see, I'll comment this part and compile the code. Now, where is the output? Dot out. Right. Oh, it is not a printable one. Okay, this was my mistake. So it is printing 8, an ASCII value. Now let's see. Now if you see, when you try to convert this structure to char, when you try to convert this structure to char, it allowed you to do it. Okay, but when you try to convert this to int, okay, it is printing some junk value. Okay, so the right way to see this is, this is what this is the memory that has been allotted, but Pi is trying to access all 4 bytes and print it. So it can have anything in it. Okay, so when you try to convert, the behavior or the result is dangerous. Okay, so hence the result is also dangerous to it. Let's see. Do you want me to try anything else apart from this, guys? I hope I'm clear on this. You guys have no doubt. Maybe you can go through these videos again and again, so only then you can understand what is the extraordinary thing this reinterpret cast, const cast, or dynamic and static cast can give you. Okay. Okay. I think that's all I had. Maybe we'll see some next time. You guys have any more doubts on this, please let me know.
No, sir.
Thank you. You guys can hear me, right?
Yes, sir.
I think 1 minute. Hello. You guys can hear me now, right?
Hello. Yes, sir.
Okay. The whole class, my speaker was connected somewhere else. Okay, good. I couldn't hear you guys. Okay, fine, guys. Okay, thank you. Thank you all.
Thank you, sir.
Thank you.